Welcome to the 11th lecture of this course, Discrete Time Markov Chain and Poisson processes. So, recall that in the last couple of lectures, in basically 3 lectures, we have talked about that heating probability. Now, in the current lecture, this 11th lecture, we will going to talk about the mean time to heat a collection of states. Okay. So, just recall again that TA we have defined to be infimum of the set n greater than equals to 0 such that xn belongs to A, where A is a subset of S, then basically in the previous 3 lectures we have talked about heating probability, which we denoted by HI, which is P of starting from I, TA is less than infinity, that we try to find out. Now, in this lecture we are going to talk about the expectation of TA starting from I. So, this is nothing but the conditional expectation that TA given x naught equals to I. We will talk about that, and again this one is also very important quantity in practice, because this expectation, as you know, the meaning of the expectation is basically mean. It is the mean time or expected time to heat the set A. Okay. So, starting from I, the expected or mean time taken by the Markov chain to heat A is given by this quantity. Okay, is given by this quantity, and the notation we are going to use K in this case. In case of the probability, we have used H notation. In case of expectation, we will use K notation. Okay. Now, so that let us first discuss what that signify. For example, in the last example, in the example we discussed in the previous lecture, that we talk about the extinct probability, that what is the probability that starting with I individual, the population will extinct, finally extinct. Okay, that probability we talk about. So, in this case, a natural question is that, and another point I should mention here is that we have pointed out that when summation gamma I is infinity, the population is sure to extinct. Now, natural question come to the mind is that, well, what is if suppose that a particular population, that summation gamma I is actually equals to infinity. So, that particular population will extinct no matter from where it starts. Now, the question is that how on average how much time it will going to take to become extinct. Okay, that question is a very natural question, and in that kind of scenario I have to find out the expectation of TA, and I start from I if I have to find out the expectation of TA. So, it is basically nothing but the conditional expectation, that starting from I, what is the average time or mean time or expected time to hit the set A. Okay, and in this case we pointed out that, well, TA can take value 0, 1, 2, so on so forth, and finally it can also take value infinity if this set is phi. Okay, TA can take these values. Now, naturally that means that this, when I try to find out this expectation, the formula of the expectation is nothing but value multiplied by probability, because it is a discrete random variable. It is a kind of a discrete random variable. Okay. So, that means I can write this one summation 0 multiplied by probability 0. So, when I talk about the expectation of TA, I can write it 0 multiplied by probability that TA equals to 0 plus 1 multiplied by probability TA equals to 1, it starts from I everywhere, plus so on so forth, and finally one term is there which is infinity multiplied by probability that TA equals to infinity. Okay. So, this way I can write. Now, this term will not going to contribute anything, because I have 0 multiplied by. So, this term is 0, this term is 0. So, I have not written this term here. I have started writing from this 1 multiplied by corresponding probability, then 2 multiplied by the probability that TA equals to 2, and so on so forth. That part is written here. that part is written here, that a for n greater than equals to 1 is summation over n pi ta equals to n. So, this part has written here. Now, the rest of the part is that infinity multiplied by probability starting from I Ti infinity, probability starting from I Pi Ta equals to infinity. Okay. So, this expectation can be calculated using this formula. Now, one thing is for sure from here, that if there is a positive probability for this, if this quantity is strictly greater than 0, then this expectation has to be infinity, because one infinity is there, it will make everything infinity. Okay. But in case, so if this probability is 0, this implies that Kia is equals to infinity. If this probability is equals to 0, there are two possibilities in this case. One possibility is that Kia is finite, another possibility is that Kia equals to infinite. So, when this probability is 0, I have both the possibilities that Ki can be finite, Kia can be finite, Kia can be infinite. That depends on what is this probability, what is this summation give me, and when this one has some positive probability, then definitely that Kia is infinite. Okay. So, that means basically we have the scenario like that. Kia can be positive, it has to be positive, because Tia is always positive. So, expectation of Ta is always positive. But there are two possibilities now. One is that Ki can be finite, Ki can be infinite. If the positive, I have a positive probability that Ta is infinite, then expectation has to be infinite, there is no other option. But if Ta is always finite with probability 1, then there we may have two possibilities, that expectation may be finite, expectation may be infinite. Both the possibilities is possible. That completely depends on what kind of probability it assigns to different values of n, that Ta equals to n, what are the probability that Pi Ta equals to n. Okay, it completely depends on that. So, this is also called the expected heating time to the state A, and informally we will write this way. Okay, informally we will write this way. So, they are almost same as before. So, let us move into example to see how we can calculate this kind of expectations. Okay, this kind of expected heating time, how we can calculate. So, this is one of the example that we have already discussed, and so that in this case basically we have 3 states. From 1 I can only go to 1 in one step. So, from 1 I will be in 1 always, from 4 also in one step I can go into 4 itself. So, from 4 I will remain, the chain will remain in 4 forever. From 2 there is two possibilities, that in one step I can go to 3, or in one step I can go to 4, both of have their half probabilities. And from 3 also the scenario are same, that from 3 I can go to 4 or go to 2 in one step, and that one step transition probabilities from 3 are half and half respectively. Okay. So, with that, now my question is that starting from 2, what is the mean time taken by the chain to get absorbed into 1 or 4? So, in this case what we try to find out, if I take A equals to 1 and 4, we try to find out K starting from some 2, K2, which is basically nothing but expectation of T A, okay, starting from 2. That's basically we try to find out. So, that is basically nothing but expectation of T A given x naught equals to 2. That is what basically we try to find out. So, to do this one, basically we define this one x I k I. So, basically this power thing I am not writing to make this notation little simple. So, a k I, which is nothing but the expected heating time to the set A, Okay. Before that, just few points I should mention in this case, more points. So, first of all, that in this case I have 3 communicating classes. I have 3 communicating classes, and it is very easy to see that 1 does not communicate with 2, because from 1 I cannot go to 2. Okay. So, 1 and 2 does not communicate, and 1 does not communicate with 3. 1 does not communicate with 4, that for sure. Okay, so 1 is a separate class. Similarly, 4 is a separate class. 4 does not communicate. I cannot, once I am in 4, I cannot go to any other states. So 1 and 4 are two separate communicating classes. Regarding 2 and 3, they communicate, because from 2 in one step there is a positive probability go to 3. Similarly, from 3 there is a positive probability to go to 2 in one step. So of course these 2 and 3 communicate. So I have 3 communicating classes in this case. Among them, this one is closed, this one is also closed, but this one is not closed. Why this one is closed? Because once I am in 1, I cannot go out of 1. 1 I am in 4, I cannot go out of 4. So these 2 are closed classes, whereas these 2 and 3 are not closed classes, because from 2 there is a possibility to go to 1, and once I go 1, that means I am going outside this particular communicating class. So that means this is not a closed class. Okay, and so that means that when I am talking about 1 and 4, I can talk about the absorption. I can talk about the absorption, because once I go there, the chain will remain in 1 or 4 forever. It will not come out from that. Okay, so with that, let us proceed now. So we defined ki, and in this case k1, which is basically, so what is k1? K1 is nothing but the expected time of hitting A starting from x naught equals to 1. Now if you are in 1, then basically if you are in 1, so Ta equals to 0 if x naught equals to 1 or x naught equals to 4, that is for sure, because if I am already in 1 or 4, that means I am already in A, so Ta is equals to 0. And if Ta is identically equals to 0, that means that K1 and K4 has to be 0. And intuitively it also makes sense, because if I am here, that means in 0 time I will be in, I am in 1. So the expectation is also 0. Similarly, the same thing happens if I am here also. Okay, so that is why that K1 and K4 are 0 in this case. K1 and K4 both are 0 in this case. So let us proceed, and what we have till now is that we have already understood what is the value of K1, which is 0, what is the value of K4, which is also 0. Now we have another 2 states, which is state 2 and state 3. So we are look for whether we can able to find out what is the value of K2 or what is the value of K4. Of course, in this case I have 4 states, so I have 4 K values. Among of these 4 K values, 2 we already find out that K1 has to be 0, K4 has to be 0. Now we are looking for what is the value of K2 and what is the value of K4. Sorry, what is the value of K2 and what is the value of K3. So how we can find out? Let us see. And the idea here, again nothing but use of the system of linear equations. So what we do? Look into this K2. So the K2 by definition is nothing but expectation of Ta given x naught equals to 2. Starting from 2, what is the expected time of hitting either state 1 or state 4. Okay, just A is basically our state 1 or state 4. So starting from 2, what is the expected time of hitting state 1 or state 4. Now what we are going to do here is that we are going to condition with respect to next transition. So we start with 2, and in the next transition I can move from 2 to 1 or 2 to 3. From 2 in one step I can move to 1 or I can move to 3. So I am going to include that particular thing here. So I write it expectation of Ta given x naught equals to 2, next transition x1 equals to 1, then multiplied by probability that x1 equals to 1 given x naught equals to 2. This is one case, and another case would be expectation of Ta under the condition that x naught equals to 2, x1 equals to 3, and then probability that x1 equals to 3 given x naught equals to 2. So, from 2 in this particular case I can move to any of the two states, either 1 or 3. So, I from 2 first step if I take to 1. So, I make the condition with respect to this and then multiplied by the corresponding conditional probability. Similarly, the conditional expectation that the first initially I am starting from 2, next transition I am taken to 3. Under that I try to find out what is the expected value of TA, and then I try to find out that should be multiplied by what is the probability that starting from 2 I go to 3 in one step. And these two probabilities are known to us, that both the probabilities are half. Now, let us talk about this expectation. Let us now talk about this expectation. Just see that this expectation I can write as 1 plus expectation of TA starting from x naught equals to 1. The first part of the expectation I can write in this particular form. Why? The idea is again the same, that if I move to from 2, if I move to 1, then Markov chain can forget the previous and it can start from time 1 afresh. Only thing is that the initial distribution will be delta 1. Okay. So, using the Markov property that at time 0 I start from state 2, at time 1 I am moving to state 1. So, using the Markov property at the point 1, using the Markov property at the time point 1, I can completely forget this one and I can start from 1. I can start from 1, Markov chain actually start afresh from the state 1. So, I can write this one, that under the condition that x naught equals to 1, the initial state is 1, what is the expected time of TA plus 1. Why this 1 is coming? Because from this state 2, when I am moving to state 1, I have already taken a one step. So, that one step will come into the expectation. So, basically when I am taking the step, this is the expected value starting from 1. What is the expected value of hitting TA? What is the expected value of hitting the states in A, plus I have already taken one step to move from 2 to 1. So, that 1 has come there. So, this conditional probability can be written in this form. It is 1 plus conditional probability, conditional expectation of TA given x naught equals to 0, multiplied by this conditional probability, and this conditional probability is given to me to be half, that in one step I can move from 2 to 1 with probability half. Similarly, the next one will be 1 plus expected value of TA under the condition x naught equals to 3 multiplied by half, because again this probability is half, and this one again starting at the time 0 I am in state 2, at the time 1 I am in state 1. So, again Markov chain can start refresh from the time 1 and I can completely forget about that. Only thing is that it will basically start from the initial state 3. So, that is why this expectation come into the picture, plus 1 because I have already taken one step to move from 2 to 3. So, I get this one. Now, notice that this particular part, this particular thing is nothing but K1 and this particular thing is nothing but K3. So, I can write now K2 is equals to half time 1 plus K1, half times 1 plus K1 plus half times 1 plus K3. So, I have this linear system. If I just simplify it, it turns out to be K2 equals to 1 plus half times K1 plus half times K3. Similarly, K3 can be written from K3, from 3 I can move to 2 or 4 in one step. So, when I am writing K3, it will be the probability of moving from 3 to 2, which is half, plus multiplied by 1, because this one step I have taken, plus K2, 1 plus K2 and plus half into 1 plus K4, because in the probability of moving from 3 to 4 in one step is half,
and that should be multiplied with 1 plus k4, because one step I can take from 3 to 4, that one step comes here, plus k4 is the expected value of Ta given x naught equals to 4. Okay? And so we now have two system of linear equations, and we can solve this. Basically we have now a system of linear equation which involves two equations and four unknowns, k1, k2, k3 and k4. Among of these four unknowns, two of them we have already found out. So if I plug in these two values k1 and k4 here, I will finally have a system of linear equations which having two equation involving two unknowns. So we have to solve that, and once we can solve it, I am done. So in this case solving is simple, because we got k3 equals to this one. If I just replace the k3, so first thing is that this term will not contribute, this term is 0 because k1 is 0, this term will not contribute because k4 is 0. So what I get is k3 equals to 1 plus half k2. If I plug in 1 plus half k2 in this k3, if I replace this k3 with 1 plus half k2, what I get is k2 is equals to this quantity, and now I have a equation in k2 only, I can easily solve, and if we solve we will get that k2 turns out to be 2. So this example tells us that on an average in 2 unit of time starting from 2, I will hit the state 1 or state 4. The chain will be absorbed in the state 1 or in state 4 on an average in 2 units of time if the chain starts from state 2. Okay? So that is the idea of solving this kind of problem, and the basic idea is almost same as that of the finding out the probability, hitting probability starting from some given state. But the only crucial point, keep in mind this one plays a role in case of the expectation, but when we talk about the probability, these one terms do not come there. So keep this thing in mind. Sometime we forget to add 1 in case of the expectation, sometime we add extra 1 in case of the probability, and that is not correct. So keep in mind, when I am talking about the hitting probability, calculation of hitting probability will not involve 1, but calculation of the expected time of hitting will involve this 1, because one step when I am taking, that need to be added to the expected value, but that need not to be added to the probability.
Now let us move and put this idea in terms of a theorem, and the theorem again looks almost same as that of the hitting probability case, only change is that again that 1. Okay? So the theorem goes like that: the vector of mean hitting times Ka, which is basically nothing but collection of all Ki's, is the minimal non-negative solution of the system of linear equations this. Okay? Again minimal non-negative solution of system of equation this, and this system of equation written exactly that way. If I am already in A, then the expected time is 0. If I am already in A, then the expected time is 0. If I am outside A, then the expected time can be written in this form. So what I can write, that Kia, I am talking about I does not belongs to A in this case. So that I can write as, well, if I can go from I to some j, then in one step, then this Pij will come multiplied by what is the time to go from I from j to A, what is the expected time from going from 1 to A, plus 1 that will come. Okay? K j A plus 1 that will come. Now this j can be anything in the state space, so that sum will come. Now because we know that summation Pij j belongs to S is 1, so that means that I can write this one as summation Pij Kj A j belongs to S plus summation Pij j belongs to S. Now this term is basically 1, so it turns out to be 1 plus summation j belongs to S Pij Kj A. Okay? Now you see that I have also written here one thing, and that is basically nothing but if this j belongs to S, if this j, Now this S can be written in terms of two sets. One is A and one is A complement. Okay, A can be written in this way. Now that means this sum can be written as plus summation j belongs to A p I j k j A plus summation j does not belongs to A, j belongs to A complement means that j does not belongs to A, p I j k j A. Now when j belongs to A, this is 0, this is basically 0 that is given here. If I belongs to A, k I j equals to 0. Similarly, if j belongs to J, k I j equals to 0. So this term will not contribute anything. So finally I have k I a equals to 1 plus this sum. That's what basically written here. Again keep in mind that when I am solving it, finally I have to look into minimal non-negative solution, the minimal non-negative solution, and the notion of the minimality is same as before. That is basically if xi is another set of solution, another solution in this case, then basically another non-negative solution in this case, then basically xi has to be greater than equals to ki, okay, kia. Xi has to be greater than equals to kia. That is basically the definition of the non-negativity minimality in this case. Okay, so that is basically the idea put in terms of the theorem, and this minimal non-negative solution is important when basically we have an infinite number of solution of this particular system of equations. Okay, let us discuss another example where we can use this theorem to find out the required quantity we are interested in. So that in this case it goes like that. It is a standard snake ladder game. Only thing is that in this case it is a 9 cross 9 square. We start from here 1 and our aim is to reach 9. It is the finishing point. We start from 1, our aim is to reach 9, and the game goes like that. I am tossing a fair coin. If head comes, then basically we will advance one step. So if head comes, we will advance one step. So when I am in 1, if I toss head come, I go to 2. Okay. If tail comes, I advance 2 step. So if I am in 1, if tail comes, I go to 3. Okay. So from 1, I toss a coin. If head comes, I go to 2. If tail comes, I go to 3. Then the standard procedure applies that if I am in a foot of a ladder, I will climb up to the head of the ladder, and similarly if I am land in a head of a snake, I will slide down to the tail of that snake. Okay. So that way the standard game will continue. Only thing is that I am tossing a coin, and based on the head or tail, I am taking 1 step forward or 2 steps forward. Okay. So that means that if I now try to write this in terms of the transition probability matrix of a Markov chain, how we can write? Look into that. First point is that suppose I am in 1, I toss the coin, I got a head. So I am in 1, I start at 1, I got a head, I move to 2, but it's 2, I will not stop, I will climb the ladder, I will actually finally go to 7. Okay. Similarly, if tails come, I will move to 3, but I will not stop at 3, I will climb the ladder and I will go to 5. So that means that 2 and 3, these states I cannot stop anytime. So in the foot of the ladder, we will not stop in the foot of the ladder. So that means this 2 and this 3, these 2 steps I do not need to consider. These 2 states I do not need to consider. Similarly, at the head of the snake, I will not stop. If I land in the head of the snake, I have to slide down. So similarly, this 6 and this 8 I do not need to consider in the states. So in the states I need to consider 1, then 4, then 5, then 7 and then 9. So I have 1, 2, 3, 4, 5 states in this case, and the states are 1, 4, 5, 7 and 9, where actually I can stay. Okay. So if I write this one now, let us try to find out the probabilities. So from 1, can I move to 1? No. if head or tail comes, whatever comes, I have to move out of 1. There is no point that I will be in 1. I will be in 1. So from 1, where I can go, if head comes, I will go to 7. If tail comes, I will go to 5. So from 1, only possibilities is to go to 7 or go to 5, and the probability of going to 7 is basically nothing but probability of getting head, and because I am tossing a fair coin, the probability of getting head is half. Similarly, probability of moving to 5 in one step starting from 1 is same as probability of getting a tail, and the probability of getting a tail is basically half. So that's why these two quantities are half, that from 1 I can go to 5 with half probability in one step, from 1 I can go to 7 with half probability in one step. Rest of the probabilities in this row has to be 0 because the row sum has to be 1. Okay. Now from okay, I am sorry, that will not be 2, that will be 4. So now from 4, where I can go? Now I am in 4. Now from 4, if head appears, now start 4, start at 4, where if head appears, I move to 5, and when I move to 5, I have to stay at 5. If tail appears, I will move to 6, and when I go to 6, then I have to slide down, finally I have to come to 1. So from 4 I can go only to 4 or to 1. Okay, from 4 I can go to the states 1 or 5, and in this case the probability of going to 1 in one step is half. Similarly, going to 5 is half. So similarly, I can write all of them, but once I reach 9, I will be 9 forever. I will not, the play will end, so means I will be 9 forever. So from 9 I can only go to 9. So I have 1 here. So in this way the matrix can be written, and once the matrix can be written, I can again write the system of linear equations. And here also the idea same. See that when I am talking about K1, that from 1 I can only move to 5 and move to 7. So that means it will be 1 plus probably P15 times K5 plus P17 times K7. Okay, so I can write this. Similarly, I can write complete equation here. Only thing K9 will be 0 because 9 in this case A is basically my 9. That is basically we try to find out heating time to 9 because I am trying to find out how much time I need on an average, how much time I need to complete the game. So that's why I try to find out basically nothing but K1 I try to find out. That is basically my aim, and I define that Ki like this, and I can write this way. I have to solve this system of linear equation, and if you solve it you will get this. Now the question is that how can you solve? The solving is very simple. In this case just little bit of algebra you have to do, because in this case you see that K9 equals to 0, so that actually do not contribute. So now this is the equation in 7 and 4. Now if you plug this 7 here, this expression here, it will turns out to be equation in 1, 5 and 4. It will turns out to be equation is 1, 5, 4. So now this 3 will be equation is 1, K1, K5 and K4. So 3 equations I have and 3 unknowns I have. I can easily look for the solution. Okay, so this way we can solve. The substitution method will help you in solving, and if you solve, finally this result you will get. One point I should specify here, look, in this case I have a unique solution. So in this particular case, that minimality I do not need to look for because I have only one solution, so automatically this is minimal. And if you solve it, you will find out this is a non-negative solution. There is no question about that. All the ki's are greater than or equals to 0 that you will get. So finally this is the solution. We are done. So what we get is that on an average about 6.625 tosses I have to do to complete the game. Okay, to complete the game on an average I have to tosses 6.625 times. With that I stop. Thank you for listening.